Hi everyone, welcome to machine learning using Python, advanced machine learning. This is the module 6, session 3, and we expect to Jamie Pasava, our instructor, to carry forward what he had left out last week, the last session on the Wednesday, where he had promised us to follow up with the various what you call the forest and other algorithms. So I will let Jamie describe and not steal his thunder. Let him go ahead. Jamie, welcome. Go ahead, take all floor is yours and continue.
Thank you. Thank you so much. So, hi everyone. This is machine learning using Python, and this is module 6, part 3, session 12. So, today's learning objectives are ensemble techniques, and within ensemble techniques, we will be discussing the random forest algorithm. Then we'll move towards boosting and discuss adaptive boosting, also called as AdaBoost, and gradient boosting. So in the previous session, we used this data set, which is from a bank's marketing campaign for a term plan. So how the subscribed column is filled, as you can see, it's the last column. So it's filled when the bank makes the call, and after the call, whether the customer is subscribing to the term deposit plan from the bank or not. So you can see the various features that are available, and also the sample of records. When we use the info method, you can see that there are a number of and it's listing all the columns and the kind of values that they take, and we have 4521 number of entries, total 11 columns. So this is just a brief of the data set that was used, because we are continuing from the previous session. Now, in the previous session, if you remember that we also used single machine learning algorithms in order to predict on this data set, and we used elastic net, lasso, and ridge regression, and got different values, and out of which lasso was the best one. But what if we want to use multiple machine learning algorithms? So in that case, we multiple machine learning algorithms together, by the way. So in that case, it's we use ensemble methods. So what are they? They are the machine learning technique that combines several base models in order to produce one optimal predictive model. Now, ensemble methods are learning algorithms that take a set of estimators or classifiers and classify new data points using strategies such as majority vote. So you can see the image below. Original data set is split into different, or sorry, I will not say split exactly, but the original data set is used in order to make sample set different sets where one record can occur in multiple data sets also. And using this sampled sets, the machine learning algorithm is used. So all the outputs given by those machine learning algorithms, by the use of majority voting, we conclude to one single output. So the majority voting could be used on counting simply the vote from which class, or it could be weighted based on their individual accuracies. And ensemble methods are also used for regression problems, where the prediction of new data is simple average or weighted average of all the predictions from the set of regression models. And also you can see that the splits are denoted by capital K, capital N, and smaller case K and both. So
What do the smaller upper and lowercase mean difference? Can you please go back?
yeah, so the capital K and capital N, they denote for the original data sets dimension of columns and rows, whereas smaller K and N denotes to the sampled set dimensions of the data set, which are uh, K for columns and N for rows. So
So, are you saying that the data set is all inclusive? That is, when you get the data set, original data set is uh, uh, k columns and rows, correct?
yes,
And so, out of that, whatever tabular view of the data set, which is data frames, we are going to select something out of it which is specific, one sample set, two sample set, three sample. Similarly, we will have n sample set, lowercase n sample set, correct?
yes.
And the lower, depending on how many, what columns are included, are the same columns are included probably, right? All
So
k
yeah,
columns.
so it can differ if we are using algorithms like uh, hello, I'm there.
Yeah, like what?
Yeah, so if we are using algorithms like random forest, we can have a different set of features.
Okay. Okay. So what you are saying is the features selected could be different, but the stress is on because you can also weigh it, right? You can apply weight,
Yes,
and therefore, what is prioritized, what is not prioritized, we don't know until we get into details. But you
yeah,
can use the same K uniformly, or you can use selectively by zeroing out the other features.
yes,
Okay, got it. Got it. Thank you.
yeah,
That explanation helps. Yeah, go ahead.
yeah. Thanks. So the continuing with the ensemble methods, when we build when we are building or using the ensemble methods, multiple classifiers are used on one training set. So instead of using the same set for all the classifiers, we use bootstrapped samples. So these samples are randomly drawn with replacement, as I said, the for this representation, that the replacement the same record can exist with different number of sample sets within different some number of sample sets. So that's why it's randomly drawn with a replacement.
So example, let's say if you had 1,000, n is 1,000,
Yes.
and small n is say 100. So which 100 is in first one, which 100 is in second one, and third sample we
So
don't.
it's a random.
It could be common, it could be different, it could it's random basically. Got it.
Yes.
Got it. Yeah, go
Okay.
ahead.
Okay. Yeah. So uh, so as it's a randomly drawn and it's a with replacement, there are chances that some of the observations cannot be will not be picked. So those observations are and then used for the testing, uh, are used as testing samples, and those testing samples are called out of bag records, which helps us for the evaluation of the models, and evaluations or models are used for accuracy, to check the accuracy of the model. So because those sets are preserved for testing, we do not need to separately have the validation set.
So are you saying that bagging is the one which is for bootstrapping, means for model building first, and then testing is separate, correct? Am I making sense? When you build a model, there is a
Yes,
process, right? Building the model, then testing the model, and then validating, right? Is
we are only talking about the data set and building the data set right now,
oh,
and
okay.
using those sample sets for the models.
So basically, sample sets is the booting mechanism, and that is
Yes,
bagging. That is your bagging at that time.
yes,
So
yes,
once we bag, after that we build a model, and then we test the model. Okay.
yes.
Okay. Got it. Got it.
So
Continue.
basically, the reason that we do this is because we want to try to avoid overfitting. So because we make these samples out of a mixed number of variations and stuff, the model learns patterns and learns to generalize them well. So in that way, we avoid overfitting. So that's the use of it. So the process of bootstrapping samples from original set to build multiple models and aggregating their results for final prediction is called bagging or bootstrap aggregating.
Okay. So
And
ultimately, it is the ensemble we want to produce of
yes,
trees, different trees in the forest.
yes.
Okay. Got it. Got it.
So
Is,
the
is this KNN same as forest and tree, or is it different?
no, no, KNN is different.
Okay, so this is like that, but it is not same. Okay, got it. Okay.
Yeah. Uh, KNN would be different. Here, random forest is used as an ensemble technique, and uh, as we move further for the session, the Ansible techniques can also be in a parallel way or a sequential way. So we'll see that further. So right now we'll be starting with the random forest, which is one of the ensemble techniques in the bagging. So a random forest is an ensemble of decision trees where each decision tree is built from bootstrap samples and randomly selected subset of features without replacement. So the same number of records will not be used again. And the decision trees are normally grown deep without pruning. So pruning is basically we remove some of the branches and leaf nodes because if we allow the trees to grow very deep according to the to fit the whole data set, it and there is a chance of overfitting. So that's why we use pruning and we remove some of the branches from the tree. So that is basically pruning. So decent trees are normally grown deep without pruning. The number of estimators or models to be used in random forest can be tuned to increase the model's accuracy. And because we are using the sklearn's random forest models, the hyperparameter or the parameter values that it takes are number of decision trees to be used, number of records and features to be sampled, and the depth and the search criteria. So when we use this uh, sklearn's random forest classifier, the number of estimators as an estimator, the criterion for Gini and entropy, and the max features. The int means max features for each tree. If float, then max feature is a percentage, and you can see that how we can use it for float values. If the max feature is auto or square root, both of them mean the same thing. And then the other feature is log 2. The fourth, the parameter is log 2 that it accepts. Then the max depth is the integer, which is the maximum depth of the tree.
So here, uh,
Yes,
Jimit, we are using Gini and what was
entropy,
that? Entropy. Okay. So those are the criteria for.
decision trees.
Okay. So are we not mixing up with decision tree and random forest, or is it individual decision tree versus the ensemble?
No, no. So basically, you can see that that is the first parameter, which is a number of estimators.
Okay.
So random forest is a group of decision trees used
Okay.
to make an output.
Okay,
So
good.
what we are doing is making simple classifiers or here decision trees, and making use of the random forest concept, and using the number of decision trees, which will be specified with the use of n estimators.
Okay, okay.
So those simple classifiers will help us build a strong model.
So each tree has a maximum feature which you will take, and that could be different for different, or is it same, fixed for everybody?
Uh,
See,
so
max it says, right? Number of
yeah,
features to be used for each
yeah,
tree. So each tree will have a fixed max, or it will have different.
it can differ depending on the trees,
Okay.
and yeah.
Okay. And then auto means it is standard square root as a
Yes, square root of n features.
square root of n features. Okay. And what is
And
this?
square root itself is also the same, it
Default.
gives the same output as a auto.
So auto means it is default. Square root is default. Correct?
I
Same as
guess
auto
that,
means what? Auto means auto. If you leave nothing, it will automatically do only square root, and which is
yes.
default basically. And if not, then you will use log2, which is the lasso, right? What was it? Other one in the decision tree.
Yeah, it was the last time in the regularization for a
Yeah.
ridge, lasso, and elastic net and stuff.
So, and the depth is the depth of the tree. So
Yes,
you will
the
not
number of
have
levels you can see.
okay levels. Okay, thank you. Go for
Yeah. So implementing the random forest with the scikit-learn's random forest classifier and giving the values of the parameter. Here the max depth is 10, and the number of estimators that we are using is also 10. And we are using it on the train X and train Y split that we have done it before. So we are fitting the data to the model, and this is the output that we get for the values. Now we are not going to use or use each and every parameter value here, but you can see that some of the values like criterion is used Gini, which is also the default value. Then max features was auto, max depth is 15 and stuff. When we so after getting this output and fitting to the data, when we draw the ROC curve for the model that we have built, we get the AUC score of 0.86, as you can see on the bottom right. Now, if we want to get the optimal parameters for the random forest classifier that we are using, then we can use a grid search in order to get the optimal parameters. And the model's AOC score is anyway better than the ones that was used in KNN, which you can see the KNN score or the KNN ROC curve is on the right, and the one that we just discussed using random forest is on the left, and we are getting the AOC score of 0.86. So as we want to know the optimal parameters, we use the tune parameters again.
can you
Use the
show back? Can you show back the
yes.
this one and previous one?
So
No,
so
previous one. Previous
yeah,
one. First the previous one. Yeah. What is this? This is Canaan's result.
no. This is for random forest.
One second, second. Can you just stick to the first one you showed was for what?
This
It's
is
your,
the
it's
random
your
forest.
operating characteristic, it says, right? ROC
Yes,
curve. But it says this is ROC, correct? This is ROC for what?
this is ROC for random forest model.
But at the AUC for random forest model 0.86, it says at the bottom, it says better compared to KNN model. That means
Yes,
first thing is this is for receiver operating characteristics of random forest ensemble which you are using, right?
yes.
Random forest, building random forest, drawing the ROC AUC curve, but this is ROC curve, right? And what is this line versus what is this line? What is the 2.2?
Sorry,
There is one dotted line. What is that
the
dot?
diagonal line, right?
Yeah, okay, that is
Yeah.
diagonal. And the
So,
other one,
so the diagonal line is showing the AUC score of zero point 0.5. So anything below
oh,
that,
okay,
it kind of becomes an unacceptable
okay.
score.
So this diagonal line says that anything 50% at least positive result will give us acceptable. Anything less than 50% is gone, right?
Yes.
Don't care. So now, if it is more than 50%, how much more than 50% is correct? We don't know, right?
And so basically, whenever we do this, it's almost always used as zero point 0.7 of zero point 0.7 as the score for area under the curve.
Okay. So basically, what you are saying is it is again going like a normalized 0.68, right? 0.68 to 7. So zero point 0.7 is considered as good fit.
Yes.
Am I getting correct? Okay.
Yes.
So in this case now, if you start on this axis, it says 0, zero point 0.2, zero point 0.4, zero point 0.6. So this is the probability.
No, no, this is the true, this is the ROC curve. So it takes the true positive rate and the false positive rate.
Okay, so this is true positive rate, this is false positive rate. So TP and FP of that
Yes.
confusion matrix you are taking. Okay, got it.
Yes.
So if you have got a false positive and true positive, so the receiver operating characteristic uh, for the random forest model gives this kind of a curve.
Yes.
Now, this is this is giving you as 0.86, correct? Area under
Yes.
the curve. So this
Yes.
area is under. So this is the total 100 by 100. So you are getting an average of 0.86.
Yes.
Like this area under this whole curve is 0.86, right? That's
Yes.
what it is. Okay. So I understand now you have said this is for random forest, but at the bottom when it says KNN, it gets confused. Okay. So
Yeah.
yeah, and
Yeah.
that is
So
yeah,
that.
that is you have blacked it out. I would rather have this being black dark, so that we are talking about this and this is just a
Okay.
comparison, right?
Okay.
You remember because immediate impression given is different, right? You put
Yeah.
the top in the black, and not the bottom in the black. That is, yeah. So people will understand that because you put KNN equal to 0.86, better than KNN. So I'm still wondering what are we talking here? Yeah, good.
Yeah.
So yeah, go ahead and show.
Yeah.
That
Yeah, sorry for the confusion.
no,
I didn't realize it. Sorry.
no. All I'm trying to understand, right? People have to
Yeah.
understand things. So random forest building, random forest model, and drawing the curve and getting the value. So you
Yes.
got it, and you are saying that uh, this is 0.86. And
Yes.
so the one other thing is random forest model point better compared to KNN model. Why is it then 0.80, right? Okay. So that is not 0.86.
No, no, it's not
So what you
pointed.
are saying is
It's
you are comparing and now you go ahead and show the second one and
yes.
now it makes
Yes.
yeah.
So, uh, so KNN models is not sorry, it's 0.84 and not
Okay.
0.80. So sorry for that. Uh, so this uh, so KNN model's curve was constructed in the previous session. So that is the reason that I'm showing this curve again. The KNN's curve is on the bottom right, and the random forest curve is on the bottom left.
So
So
can you put there somewhere to say this is random forest and this is in the bottom in the because comparison when you do people don't see.
okay,
Yeah, just add that. So say random forest here random forest, and yeah, and on the other one you put it as KNN. Yeah, that should suffice. Okay, done. Yeah, thank you.
Yeah.
Yeah, so we know that we are talking random forest has got a 0.02 better than the KNN.
Yes.
Close, they are close. I don't think they are that distinctive, but anyway, that
Yes.
depends on how you assemble the random forest. Yeah, go ahead.
Yeah. So so continuing with the so after knowing that we got a better score for random forest, we'll try to get the optimal parameters. So on the random forest model that we have built. So getting the optimal parameters, we'll be using the grid search CV, basically K-fold cross validation, and we'll be using the estimators for the max depth as 10 to 15, number of estimators from 10 to 20, the max features for auto or square root and point 1, point 2, and the grid search CV values, the CV value is 5. So when we fit the model for the splits that we have made and get the best score, we get the score of 0.94, and the uh, for having the optimal param or the best parameters, the max depth value of 15, max features as auto, and the number of estimators as 20. So
These are all for random forest, right?
yes,
Okay, so you are trying to get the random forest to optimize for better accuracy,
yes,
and it was 80.84. Now you are trying to hit a 0.94 with that variation.
yeah, with the help of this grid search, we got the score of 0.94.
Now, what
Now
is this? Research CV means CV or
it's
anything?
a K-fold cross validation, where
Okay.
data set is split into a number of CV
Uh,
uh, value allocated. So here the CV value is 5. So the data set will be divided into 5 parts, and then with every iteration,
mhm,
it will be trained on the 4 parts, and the fifth part will be used for
mhm.
testing purpose.
Okay.
And so that's a K-fold cross validation in
So
short.
when you say 5 segments, that means if you have, uh,
Yes, a data set being divided into 5 segments.
so data set means the whole entire data set
Yes,
or the samples. So data set is created from the data set, 5 samples are created, correct?
yes.
And those 5 samples, do they cover the entire data set or they are just some uh, something
So
less than?
they are uh, built and with and so there was a k-fold cross validation uh, a diagram also. I don't know whether I have this in this slides or not, but basically it divides it into 5 parts in a column, and then 5 iterations of the rows.
For it.
So, and for each iteration, the 4 parts will be used for training purpose, and the fifth part will be used for testing purpose
Okay.
in that iterative manner.
And so for each iteration, it will be 4 plus 1, 5, 4 plus 1, 5. And they
Yes,
will all be staggered, right? It will not be the
yes,
same four and same rows and same column. The row may change, right?
yes,
Okay, got it. Some staggering, some randomness is there in that. Okay, got it.
yes,
Okay, so grid search CV is based on the segmentation of the actual data into sample data, which are numbers reflected here, 5. And
yes,
accordingly, you are having the rows and the columns or whatever you call it under the data frame. the rows and the columns, and then you are doing something optimized so that you are getting a better uh, result, area under the curve or region under the region over the curve, receiver received uh, whatever ROC, what you mean, and then
Yes.
that's what you're getting. Okay, got it.
Yeah.
Thank you.
Okay.
Continue. I just interrupted to make sure that clarification is there.
Okay. Sure. So, um, so after using the optimal values for get training your model again for the random forest classification and drawing the ROC curve for that for the optimal values, we are getting the AUC score of 0.94 now, which is a good improvement compared to 0.84, 0.86. When we draw the confusion matrix for this model of optimal values used for the random forest, this is the confusion matrix that we get, which is predicting uh, 464 true values on actually subscribed and 111 for falsely predicting as a not subscribed out of 575 values. And we also have a good recall score and F1 score and precision score as well.
Can you go back and explain what does F1 score and recall score and what is this precision and all that?
Uh, yeah, so sorry.
Go ahead, just explain this, just what this means, the columns which are there. And
Okay.
this is sum of the two, right? False positive, sorry, uh, subscribed. The first quadrant, second quadrant is subscribed. And what is first quadrant? 110. Which is which is positive, which is negative, which is false. So your confusion matrix quadrant is this is the x and y, right? At 600.
Yeah. So so below so in the horizontal way, there are these are the predicted subscribed and not subscribed, whereas on the vertical line or the y line, and those are the true labels uh, for the values that are actually subscribed and the values that are not subscribed.
So 464.00 is truly subscribed, true and subscribed.
Yes.
False, positive. Or is it true positive?
No, no. 464 are true positives.
True positive. Okay. So this is true positive. And what is this? This is false
The
positive.
111 are
False
uh,
positive.
fa-
False positive. Correct?
yes, I think for false negatives.
False negatives. Okay. Okay. So, no, how do you calculate this? That is what the whole formula is. Your class, this, the definition of uh, each one is different, right? All the scores and all. So one is true positive upon true positive plus false positive, right? That is one of the measures. So I don't know what this recall and F1 and precision. There is no indication here is what they are. So it's difficult to interpret. I would suggest that if you have any formula associated, if you can pointer here, and pointer here, whatever. Precision means what? Recall means what? FP over TP plus TP, FN over this. At least have some uh, uh, projection here on the text boxes later, okay, not immediately, so
Okay.
that one can understand what are you talking here. Because drawing confusion matrix and reading this prediction, it's all fine. But what is this meaning of this confusion matrix and what's what? If you cannot explain, at least you should have a because it's difficult to for people to comprehend without having the formula. So what you do is add to the formula in the slide so that people can understand. Those who have attended previous session, they should follow, but still it's a iffy, right? Whether they will understand. And you're skipping and going to the next without explaining, it will be hard. So I would say, I want here, what does precision mean? What FP by TP or whatever, or TP by FP plus TP, recall means what, F1 means what, there should be here something representing. And then in this graph, it should say this is FP, TP, TP, FP and whatever, and whatever these four, they should be, besides the number, there should be what is it representing. Uh, it's hard for people to comprehend otherwise. Okay. Anyway, go ahead. I'm done with my feedback. You can add that and put it in the. Okay, go ahead.
Okay, so
Yeah, continue. Continue. Right now, you continue.
Shortly speaking on the classification report, when we give the get the classification report, we get the precision, recall, and F1 scores. So precision is basically true positive divided by true positive plus false positive values, and all of these values, are they lie between 0 to 1, and we are getting very good values on the predicting not subscribed, but we are also getting good values on predicting people who have subscribed. Now not subscribed is denoted by value of 0, and subscribed is denoted by value of 1.
Jamit, can you add the text here, TPFP and all that, at least here, and add the text here so that while presenting itself, people are understanding. We can wait, no hurry, no hurry. Just keep adding that, figure out from the past whatever you have, and add it here because this is recording, right? People will
uh,
listen to the recording, they will not understand this unless you put that. So do keep this as is, and the background, go ahead and fix this if you can. Or we can hold, no hurry. Okay, yeah. Just do it online, no problem.
Sorry.
Yeah, while Jayamit continues to fix the slide so that everybody can understand, I will just say this confusion matrix is very important in this most of the uh, what do you call the statistical measurements one we takes, and in machine learning this is a very very important matrix. So everybody should understand uh, what is positive, false negative, and true negative and false positive and all that. And what happens is, this is we are talking about data samples, and so the samples uh, are drawn out of the population. So your population is the entire data set, and for either it is a KN or whether it is for the small KNs which he described earlier, as well as for the random forest, he's picking up some of the numbers that are for the samples. And within the sample set, you are doing for individual runs, and then ultimately you are aggregating. Ensemble is an aggregation, and therefore it is a aggregation he's bringing. So when he draws the confusion matrix of the predictions of the dependent variable based on the independent variables. So X is your independent and Y is your dependent. So while doing that, uh, it comes out with the different confusion matrix here, which shows that some people subscribed, some people did not subscribe, because this was the related to the banking where subscription was the idea. Who are all subscribing and who are not subscribing, and based on the subscribe whether because the data set was for getting to subscribe for a particular bank, I believe that was what, that's why it is subscribed and not subscribed. And the predictions were obviously based on the label, and the labels, uh, what were the labels, and what were the true positive reflection and uh, false negative. That is what drives the ratio. So you can go and fix the precision, recall, and FN score. These are the three where you can just base it on the TPFP, TNFN, I believe. Precision is based on uh, some average of some TPO or something exact detail you can put in. Same way for recall and F1 score. You can look at the various things what you have done in the past and add those meaning what they mean. Obviously, the reference is always going to be no. You may not have to describe TP is T positive or something. That's fine. All we want is the precision. What does it mean? Yeah, good. What is precision meaning? And Tn by, yeah, those formulas are important. Otherwise, it makes Tp by Tp plus Tn, or what is it? T plus,
False positive.
okay, Tp plus Fp. Okay. So this is what we, when we say precision, that's what here it is. And F1, obviously, F1 score is the one which uh, is it a square root or something?
No, no, no. 22. Recall value.
Recall value. And what is recall? Recall is another.
It's a yes. It's a. I'll
Yeah,
write down the
twice the recall and then into
uh, precision
precision. And then recall and precision will be,
divided by
yeah, 2 into recall into precision divided by,
plus
oh,
precision. Uh,
see, this is complex, you know. So if
yeah.
people understand, then they will say what this meanings. See, the problem with this, all this scikit and all, they will just assume things. Okay, you assume things, but people have to understand, right? What have you drawn? Recall is equal to TP by TP plus false negative. Good. So, which is negatively false. Basically, it should have been, but it is not, right? Positive.
Yes.
So that means TP plus Fn is the actual overall gives you the uh, what is recall, and then once you get recall, then you want to know what is precision of it, and precision is again TP by TP plus Fp. So you got two measures, recall and precision, and then you are combining both of them to arrive at a F1 score, which is the combination of the recall plus precision. So how you calculate is all, and this two is within outside the bracket or inside the bracket? How is it? Two into recall. How,
Yeah. It's all the fall and these term are all numerator. Wait.
okay, so that is new. So put it under numerator. Yeah, that is, and then put a star between two and recall, like you have done for recall into pre.
Oh, okay. Okay. Okay.
Put that in. Otherwise, assumption will be wrong. So what you are doing is twice the recall into precision divided by recall per precision, right? So that is the one which is actually calculated. Now you can tell, put it on the full screen and then explain now. Yeah, go ahead. So drawing the confusion matrix was a, yeah, good process. Fantastic, good job. Good. So now explain where we left.
So
So you can go back to previous page and come back so that we know where we started. Yeah.
so the okay. So now we use the random forest classifiers optimal values that we found out, which were 20 estimators or n estimator values and the max depth of 15 and the maximum number of features as auto. When we set these parameters values as so, we get the optimal result. So when we fit the value for the model that we have built for these optimal values and create the area under the curve score, or sorry, the ROC curve,
Region or no.
and the getting the AOC score of 0.94 for the optimal values that we have used. And then after that, when we create the confusion matrix and see the uh, efficiency of model on predicting the actual values or the true positive values. And these are 464 were predicted correctly by the model out of 575 values. And when we use the classification report, we get the precision recall and F1 score. You can see the formulas for recall, which is TP divided by TP plus FN, precision for TP divided by TP plus FP,
Can you
and
put it into bracket the TP plus FN parenthesis? Otherwise it gives a same way there also. Okay. Yeah.
yeah. So
So when you said you had 576, that is 464 plus 111.
yes, 575.
That is equal to TP plus FN, correct?
Yes,
So recall is nothing TP by TP plus FN, and that is what is projected, and that is what is on the confusion matrix as well as in the column here of the
yes,
precision and recall and the F1 score. Yeah, go ahead, continue. I think you continue with the recall. Start with recall.
yeah. So we got the precision recall and F1 score values on predicting who subscribed to the term deposit plan, which is denoted by 1. When a customer is not subscribed, it is denoted by 0. So our score of predicting the values of who subscribed can also be increased, has also increased by using the optimal values.
So one is for what? Who subscribed?
Yeah, people and yeah,
One is for
people
the
who are subscribed, and the scores regarding and the scores regarding those,
so
and
0.86 is the
0.
one which was a correct one, right? 0.86 actually subscribed, and they were the that is the precision of subscribed,
Yes, predicting at people who subscribed,
and 0.81 is the recall.
and
Value.
0.83 is the F1 score.
Okay, and 0.83. So the important factor here is point F1 score is important, right?
Yeah, so F1 basically combines the values of it uses values of both precision and recall
Okay, okay.
and give us the a combined score of both of them.
So what mistakes we made and what mistakes we did not make, both are included.
Yes,
And therefore that 0.93 and 0.83 average is around zero point 0.9. That's the guesstimate, right? Or estimate rather, projected values. Okay,
yeah,
makes sense now. I think that will be good for people to understand, and because this confusion matrix is hell of a confusion unless you focus properly on what it means. And go ahead,
yeah,
Jamit, go ahead. Thank you.
yeah. Now finding the important features in the random forest algorithms. If so, the For finding the important features, the scikit-learn provides us something called as a feature importances, which provides us with the important features that are present. But just in case, if you want to know how it is calculated, the feature importance is calculated for a feature by multiplying error reduction at any node by the feature with the proportion of samples reaching that node, and then the values are averaged over all the trees to find the final feature importance. So when we use the feature rank to store all the values from the data frame of using the uh, using the features from the train X splits and all the columns and saved it into features, and then using the random forest classifiers feature importances and stored it into importance. Then we uh, sort the values in the descending order by giving the ascending values as false. And when we plot the figure using the bar plot, we get this bar plot, and you can see that balance, age, and previous campaign are the most effective features or most important features. If we go for top 5 features, then we can add current campaign and having housing loan equal to yes or no, equal to yes, sorry. So if a customer has an housing loan, then it is that customer is more likely to subscribe to the term deposit plan. So the importance score is normalized and shows the relative importance of features. Then they will be using the cumulative sum in order to know that how much data it captures. So when we do the cumulative sum for the amount of data that it captures, you can see that for the first three uh, three features, it goes to almost 60%, or to be precise, it's 58.6%. And if we add two more features, which adds to 69 and then to 74, we are almost having 75% of data being covered because of those important features. And after that, the gain is very low on adding the features. So the important points regarding the random forest important features. The top 5 features provide 75% of the information, and because we can remove some of the features basically which does not impact on the model's predictability, we can remove some of the features, and that's why this can also be used as feature selection. Now, random forest being a black box model cannot be interpreted, but it can be used to select a subset of features using feature importance criteria and build simpler models for interpretation. Now we'll be using boosting. Let's go through the random forest first. So we use the random forest classifier in order to build our model, train the model, and fit to the data, and we got this ROC curve and got the area under the curve value of 0.86 for our random forest classifier. Then we used to use grid search in order to get the optimal values, and by using the grid search, we got the optimal values of n estimators as 10 to 20, the max features as square root or auto, and max depth of 10 to 15. Now, this is showing because less number of estimators were used. So what I want you to do is increase the amount of depth and estimators and see which are the ones that gives you the best results. Now, for the model that I've trained, the best score that I got is a 0.928, and the best parameters that were there were 15, square root, and n estimators as 20. Now building the random forest classifier model with optimal parameter values, the the AOC score that we get is 0.94, and you can see the confusion matrix that we have used is this. So uh, you can see the model is good at predicting 492 predictions, getting right out of 575 values. And this is the classification report, and these are the precision, recall, and F1 score. Now, as I said that uh, a scikit-learn has important feature importances, which helps us to get the important features. And when we plot the graph for getting the important features, balance, age, previous campaign, current campaign, and housing loan, yes, are the most important features for us. And this is the cumulative sum that we have used in order to capture almost 73% of the data with the help of the first 5 features. So now we'll be starting with boosting. So boosting is a powerful technique in machine learning that improves model performance by combining weak learners in a sequential or a parallel manner. So parallelly, random forest is the one that uses a parallel approach. It In boosting, it belongs to the family of ensemble methods, which leverage the strength of multiple models to create a stronger and more accurate predictor. Uh, and data scientists train machine learning software called machine learning models on a labeled data to make guesses about unlabeled data. A single ML model might make prediction errors depending on the accuracy of the model. So if the model is trained on identifying cat, and if it's shown, if it misidentifies black cat, the boosting tries to overcome this issue by training multiple models sequentially to improve the accuracy of the overall system. Two most widely used boosting algorithms are adaptive boosting and gradient boosting. Weak learners. So there are weak learners. Weak learners are basically models with a low prediction accuracy. You can say almost smaller than 0.5%, 0.50% of it, 0.50% of it. So they are prone to overfitting, and they can't classify data that varies too much from their original data set. Now, strong learners can be made.
Even 0.05, right? We
Yes.
are not 0.50. Okay. Weak learners are 0.05 types out of
No,
the.
they have a very they have the accuracy of less than 50%.
Okay, they have accuracy of 50%. Okay, less than 50%. Okay.
Yeah.
Okay.
So boosting converts a system of weak learners into a single strong learning system. So to identify the cat's image that was misidentified, we can combine number of weak learners to train for recognizing a cat's image with pointy ears and different colors and different shape of the eyes of the cat. And after analyzing the animal image for pointy ears, the system analyzes one again for cat shaped eyes. So this which improves the system's overall accuracy as we are focusing on different parts of the cat's image to train the model. Now, how is boosting carried out? So boosting is carried out with at the beginning, it's carried out with the equal weight to every data. So at start, each data point is given equal importance. We feed this data into the first model, often called as base model. So this model makes the prediction for each data point. Then we move to the adjusting the data, the weight based on the errors made. After making predictions, we check where the model went wrong. We increase the importance with the help of weight of the data points where the model made bigger mistakes and giving more importance to model that makes better predictions. Passing the weighted data to next model. Now we send this adjusted data to the next model in the line. As it's a sequential one, we get a better model with each model, or we can say that each model is correcting the errors of the previous model. So we repeat and improve until we get a model where the overall error of the model is minimized and it's an acceptable range. So adaptive boosting is one of the boosting techniques which uh, uh, which tries to self-correct in every iteration of the boosting process. So it initially gives the same weight to each data and then uh, assigns the weight to the ones and that to the data points where it is needed and gives more weight to the incorrectly classified items to correct them for the next round. It repeats the process until the residual error or the differences between the actual and the predicted values fall between within an acceptable threshold. You can use adaptive boosting with many predictors, and it is typically not as sensitive as other boosting algorithms. This approach does not work well when there is a correlation among features or high data dimensionality. Overall, the adaptive boosting is a suitable type of boosting for classification problems. Mathematically speaking, for getting the uh, prediction on the f of xi, we it so as the mathematical representation contains the summation of from k equals to 1 to k, alpha k fk of xi for that individual observation for all the k observations. The ending sign of the uh, summation will tell us how uh, what the output means. So here in the it is k is the total number of classifiers. Fk of xi is the output of weak classifiers k for input feature set of xi, and alpha k is the weight applied to the classifier, and alpha k is given by 1 by 2 log of 1 minus epsilon k by epsilon k. So the final output of xi is just a linear combination of all the weak learners, and the final decision depends on the sign of the sum. So sklearn also provides us the adaptive boost classifier, which takes the parameters base estimator, number of estimators, and learning rate.
Jamit, what do you mean by signs in the previous slide when you mentioned depends?
Yeah.
What is the sign related to? Positive or negative? What is it?
Yes. So uh, the signs can be positive or negative due to the summation,
Mhm.
and
Go to the previous slide.
yeah.
So here you are getting a positive or negative sign. There is no
Yes.
squaring here. So it doesn't matter. So you are going to get only negative or positive, and sign of that matters. So the
Yes.
adjustment is either positive or negative based on that. These
Yes.
are adaptive, right? These are only for uh, making the precision better, right?
Yes.
Okay, so it can be a positive boost or a negative boost, depends on what you get.
Yes.
Okay, got it. Go to the next one.
Yeah. So adaptive boost classifier, it takes a base estimator, n estimator, and learning rate as the parameter. The base estimator is the base model that we use. So the base model from which the boosted ensemble is built. The base estimator should have the capability to utilize differential weights for samples, like decision tree or logistic regression. And the estimators, we have also used it before. It's the number of maximum number of models or estimators at which the boosting algorithm is terminated. And if there is a perfect fit is found, the learning procedure is stopped early. By default, the value is 50. The learning rate, it contributes to the uh, contribution of each classifier specified by the learning rate. So there is a trade-off between the learning rate and the n estimators, and default value of learning rate is 1. So the value of learning rate can affect the can be affected by the value of the result basically can be affected by the value of n estimators and learning rate. So first, we'll be using the logistic regression model, and using that logistic regression model, we'll be using uh, we'll be using the adaptive booster classifier on that for 50 n estimators when and we fit the data for the train X and train Y. And again, when we build or get the ROC curve for this adaptive logistic regression used on adaptive boost, we get the area under the curve, a score of 0.71, which is, by the way, low from all the models that we have discussed till now. We are getting almost 0.86, 0.84, and 0.94 also. Now, apart from adaptive boosting, there is something called as gradient boosting also. So gradient boosting is similar to adaptive boosting, uh, which is a sequential too, but uh, in uh, In gradient boosting, it basically does not use weight, but it tries to minimize the loss function. In adaptive boosting, it used weights on the misclassified items to get the job done for getting the uh, better model. So gradient boosting optimizes the loss function by generating base learners sequentially so that the present base learner is always more effective than the previous one. And it attempts to generate accurate results initially instead of correcting errors throughout the process. So gradient boosting can lead to more accurate results and can help with both the classification as the regression based problems. So, as also mentioned that before that gradient boosting use uh, tries to minimize the errors made by the previous model, and both of them are sequential ones, the adaptive boosting and the gradient boosting. The gradient boosting focuses on misclassified examples and the making the model gradually improve on making the predictions and also more accurate over time. So to minimize the errors, gradient boosting uses a gradient descent algorithm in each stage, adjusting the parameters of the models to minimize the loss function. Typically, decision trees are used as the base classifiers in gradient boosting, and iteratively strengthening the model by uh, generating the accurate results again and again with weak predictions and minimizing the error using the uh, gradient descent approach. So the final prediction here is given by summation of from k equals to 1 to capital K alpha k into the prediction for that particular record denoted by xi. So fk of xi. Here alpha k is the learning rate or the accuracy of the model k, and as also mentioned before in the uh, explanation of the gradient descent, the first model that it f1 of x is used, then in the next model it will minimize the uh, it will try to minimize the error again. So y minus f1 of x, which will be given to the further model for f2 of x, and those steps will be repeated until the final model is used to make the final predictions, which will have the minimized number of minimized residuals. So we'll be using the gradient boosting classifier from scikit-learn, which takes n estimator, max depth, and the max features. So the number of boosting stages to perform the default value is 100, and the max depth is of the individual regression estimator, uh, which uh, which is the limit the number of levels from the root node in the tree, and the max features are the number of features to consider when looking for the best split. So we'll name the model as GBoost CLF, and we'll be using the gradient boosting classifier. Give our n estimator values as 500, max depth as 10, and fit the model using those values. And when we check the ROC curve for the model that we have trained, which is AdaBoost, we get the AUC score of 0.98, which is the best metric that we best score that we have gotten for all the models. But we also want to check whether it's overfitting or not. So we'll be using the K-fold cross validation to check the model's accuracy. So we use the mod. So in the CV scores, you can see that we can use the cross-val score, the model that we have built, the X and Y splits, the CV value of 10, and the scoring metric of ROC AUC. So when we get the CV scores, we get these 10 scores, and we will just simply calculate the mean of these CV scores. And by calculating the mean, we get the uh, mean accuracy of 0.96, or you can say 96.8%. So building the confusion matrix on the model, you can see that it's having a 442 correctly predicting on subscribed people, whereas it's incorrectly the false negative values of 33. Here, the when we using the classification report, we get the precision, recall, and F1 score, which are almost so recall scores are 0.94. The precision score is 0.89 for uh, predicting the subscribed customers, and the F1 score of 0.91. So now getting the important using the feature importances over this GBoost model that we have used for the for making the classification, and using the graph to plot bar plot to sort the most important features above. This is the bar plot that we get for getting the most important features. Balance, age, current campaign are the most important ones. If we include top five, then housing loan, yes, and job management are the other two.
Jamie,
So
this is not the same data which you used previously for uh, subscription.
yeah, this is the same.
So, are there any differences in the top five, or is it
Yes.
similar, same?
So balance actually the similarity is balance, age, and current campaign. The values on a house loan, yes, are a bit different for gradient boosting and adaptive boosting. A bit
And
different, but not they are still in the
same order.
top
And
five important features.
what about house loan? No, no. Sorry, job management. Is it that part of
Job
that?
management is it is considered by gradient boosting over here, but job management was not there in the adaptive boosting and stuff.
Good, good. So they are different. And
Yes. So these are the important features that we get for these for using the gradient boosting. So I'll just summarize this today's session using using the code. So we stopped at the cumulative summary used, and then we have to start with the adaptive boosting. So we started with the adaptive boosting on the logistic regression model, made the fit the model with the train X and Y split, draw the ROC curve, and In this, you can see that I'm getting the AUC score of 0.69. When using the gradient boosting, yeah, so when using the gradient boosting on the train X and Y split, number of estimator values of 500 and max depth as 10. And after fitting to the model and drawing the ROC score, we are getting the value of 0.97. And because it's a very high value of AUC, we wanted to check for the overfitting. So we checked for overfitting using the uh, grid search or cross-well score. And we, after getting 10 different values, we calculated the mean, and the mean that we got is 90, 0.968 or 96.8% of it. This is the confusion matrix relating to the gradient boosting model that we have built. And the classification report for the model. And and using the feature importances on the model used, balance, age, previous campaign and current campaign are the ones and that comes at the top. So we started this session on the ensemble techniques, and one of the ensemble techniques that we used was a random forest, where we got the AUC score of 0.94. Then we discussed about the boosting techniques, which were adaptive boosting and gradient boosting. Adaptive boosting used weights in order to correct the model. Gradient boosting tried to minimize the error with each sequential models. So for adaptive boosting, we got the AUC score of 0.7, and for gradient boosting, we got the value of 0.98. When using the k-fold cross validation method in order to check for the overfitting, we checked it for CV value of 10, and then we tried to after getting the using the CV value of 10, we averaged all those values, and we got the score of average score of 0.968 or 96.8%. So these are all the references used for um, the whole module 6. And so, yeah, this was it for module 6. Thank you.
Hey, thank you, Jamie. Excellent job. And it's under 1.5 hours. And fantastic. And the coverage was very good. And maybe you can update the slides to include that on the other slides, the false positive, etc., on those confusion matrix parameters. And excellent. And hopefully people will enjoy this lesson and learn how to set the features, how to prioritize features, whether to use AdaBoost or whether to use gradient descent. And then depending on their use cases, they can apply. And I hope Jaimit has done good justice to this. So we look forward to the next session on that is on the Monday. And I don't know, Jaimit, do you have any idea what is the coverage?
It would be on clustering.
Okay. So thank you very much. So we can look forward to the clustering and maybe something on the SVM, I believe, right? Some later.
Yeah, later.
That will be later. Okay. So I think the next week, since we have got three presentations, we will be able to sort out the detail with Jaimit. And thank you very much. And keep learning and please keep coming back. And we thank you very much for the efforts from the study circle and study AI, ML using this is ML using Python. 101. And so, uh, thank you very much, Jamin, and I'll stop
Yeah,
recording.
sure.